Okay, so this will be the longer video where I go over the new notes, and so I just want you to know that there is a note catcher right here, this HR note catcher. So you should open up this document as I go forward and fill it in as I go, and then when you're done with this, this is the assignment that we will be finishing in class next time. So you have access to both of those, but make sure you open up this note catcher and fill it out as we go. So first off, we're going to start off with the sun. So the sun is a G2V star. That just means it's an average, ordinary white star. And you don't really need to know any of these numbers. I'm just going to give you a little background on it as we talk about stars, just knowing that the sun is not extraordinary in any way. It's made of the same things as other stars. It's a fairly small star, actually. Most of the stars in the universe are actually slightly smaller, but there are many, many, many bigger stars than the sun. So this is kind of interesting right here that the 99.85% of the mass of the solar system is contained within the sun. The remaining 0.15% makes up all the planets, moons, asteroids, everything else that we see. Um, the density is slightly greater than water, so we tend to think of the sun as being this big ball of gas. But it's interesting to note that it's actually more dense than water, even though it's made of the two lightest elements that we have. So um, it is clearly very compressed under a lot of pressure, and the surface of the sun would be more like a pot of boiling water rather than what you might think of as being like a gas body. Um, this right here, this is the magnetic. So here's Earth, here's the sun, and this is just showing like these particles coming off the sun. This is the solar wind. When the solar wind, which is made of charged particles, hits our magnetic field, um, the particles stream to the north and the south poles, and then they can funnel in around the magnetic field lines, and that's when we get the aurora borealis and the aurora australis. So the lights that we see in the sky are actually caused by particles from the sun striking our atmosphere. Okay. Coming over here, this is a really important part of what we're talking about. The source of energy for the sun and any star is thermonuclear fusion. Okay. And then here is Einstein's very famous formula, E equals mc squared. And so this formula says that energy is equal to mass times the speed of light squared. And so what that tells us is that a small amount of mass can become a large amount of energy because we're multiplying that mass times the speed of light, which is a very big number, and then we're squaring that. So you get a huge amount of energy from a small amount of mass, which is why nuclear bombs are so devastating. They convert mass directly into energy. Okay. Um, Again, not something that you need to know, but every second of every day, 600 million tons of hydrogen are converted to 596 million tons of helium. That means that the sun loses 4 million tons of mass every second of every day. And it's been losing that amount of mass for the last 4.5 billion years. And it will continue to lose that amount of mass for the next 4.5 billion years. Um, and so that's just a huge amount of mass. And that mass, again, becomes energy according to this formula right here. So this is just a diagram showing you that deuterium, which is an isotope of hydrogen, and tritium, which is an isotope of hydrogen, when they fuse together, they form helium and a neutron, and the pieces that make up the deuterium and the tritium isotope weigh more than the helium isotope and its neutron over here, and so the loss of mass becomes energy again according to E equals mc squared. So now we're going to move on to stars. And so looking beyond our solar system and looking out into the universe, we're going to look at the properties of stars. So we're going to talk about their brightness, their color, their temperature, their mass, their size, and their distance. So I just put three stars here for you to look at. And um, there's some information we can gather from just looking at these three stars. So one is that the colors are different of these three. The smaller one here is red, the middle one here is yellow, and the large one here is blue. We'll kind of delve into that a little bit as we go forward here. So then this picture up here shows the sun. The sun, compared to many of the stars out there, is tiny. There are stars that are huge in comparison. But again, the majority of stars out there are actually much smaller than the sun. Okay. All right, so we come over here. This is something that we can't do, but it's a term that we're going to refer to called absolute magnitude. And the absolute magnitude is the actual brightness of a star. So if stars could magically be placed 10 parsecs away along this line and we review them from Earth, we could compare the true brightness of the star. And so if I were looking at these stars right here, it should be fairly obvious to you that this big red one here, which would be a red supergiant, is probably going to be the brightest star that we would see. And very close to that would be this blue one right here. And you might say, well, this blue one's way smaller than that one. But try to remember that blue is a much higher temperature star. And so this would be a more intense light that's being given off than this star right here. So they would probably be pretty similar in brightness, although this one would probably be a little bit brighter. You probably can't see, but I put a little teeny tiny star right there. This would likely be the dimmest star. This one would be a little bit brighter, and this one over here would be fairly dim as well. So again, this would be referred to as absolute magnitude, while this one is showing apparent magnitude, how bright a star appears to be when viewed from Earth. And so again, there are these big stars out over here, and then I have some small ones over here. But if I were to say which of these stars would appear the brightest from Earth, I hope that you would say it was this one right here. And the reason this one would appear to be the brightest is it's nearly on top of us. So the sun appears to be the brightest star. It's not particularly bright, it just appears to be that bright because it is so close to us. So when we come over here, and again, the brightness of a star depends on three things: how big it is, how far it is, and how hot it is. So then the brightness of a star can be broken down into two different ways of measuring brightness. We can talk about the apparent magnitude, and we can talk about the absolute magnitude. So the apparent magnitude is how bright it appears to be from Earth. And so all three things that we just mentioned come into play. How bright it appears from Earth is going to be a function of how far it is, but also how big and how hot it is. This is a really annoying thing, but a really important thing. The smaller the number, the brighter it is. Okay. So if I had an apparent magnitude of 5 and an apparent magnitude of, say, -2, the -2 is brighter. Okay. So negative numbers are really bright, and the more positive the number, the dimmer it is. Same holds true for absolute magnitude. Remember, the absolute magnitude is the true brightness of the star. And so if viewed from 10 parsecs, um, 32.6 light years, this is an indication of how bright the star actually is, and only depends on how big and how hot the star is. But once again, the smaller the number, the brighter it is. Once again, negative numbers are much, much brighter. So then right here, if you know the absolute magnitude and you know the apparent net magnitude, what can be determined? Well, this one here depends on how big, how hot, and how far. This one only depends on how hot and how big. So if you take the difference between them, you get the distance. And so this right here is, if you know the apparent and absolute magnitude, you know the distance of the star. That's a C, I promise. So then over here, the luminosity is just another way of talking about the brightness of a star. Compares the brightness of a star to that of the sun. So something that had a luminosity of 1 would have the same brightness as our sun. And then for this one, the bigger the number, the brighter, and the smaller the number, the dimmer, which is the opposite of absolute magnitude. Okay. So we should already kind of have this down pretty well. The color is determined by the temperature of the star. And I think most of you already know that a red star is going to be a cooler star, somewhere around 3,000 degrees Celsius, whereas a blue star is going to be much hotter, about 30,000 degrees Celsius. Okay. This is a really important thing to look at right here. So we see that we have this little red star, and then as we progress this way, the stars are getting bigger, but they're also getting hotter. So this little red star here, and then all the way down to this big blue star over here. So this would be an indicator of the mass of the star. So as we're increasing the mass of the star, they are burning hotter and faster, and so the temperature will be determined by the mass and size, whereas more massive stars burn faster and hotter. So this is also going to be a little counterintuitive in that this big blue star here, it's got lots of fuel, but it will burn out much faster than this little red star over here, which has very little fuel. So again, this star over here might live to be, 100 billion years. Oops, that's a billion there. And kind of progressing this way, this star might only live for 100 million years. Okay, so a huge difference in the amount of time that they will be able to fuse. And then here is a star like our sun, and this one would be about 10 billion years, so somewhere in the middle of those others. Okay, coming over here, this is a really important document as far as identifying the evolution of stars. So we have what's called an HR diagram that plots stars according to their absolute magnitude or luminosity and their temperature. So on the one side over here, I have their absolute magnitude. On the other side, I have their luminosity. And then on the x-axis down here, I have their temperature in Kelvin. Um, the weird thing about this graph is that it's kind of backwards. The higher temperatures are on the left and the lower temperatures are on the right. Um, so if we were to plot a star like our sun is about 6,000 Kelvin, which put it about right here along this line here. And then its luminosity would be 1. So a star like our sun would be right about here in this HR diagram. So a couple things kind of pop out at us when we plot stars according to their absolute magnitude and temperature, that there are distinct kind of bands that develop. So right over here, this long little stretch here is called the main sequence. So this represents a place on the diagram where stars are in what's called the stable state, where the forces that are acting on those stars are balanced. This is also where a star is fusing hydrogen into helium. And there are huge differences in the stars along this line here. But one thing they have in common is that they are all stable and they are fusing hydrogen into helium. Okay, so if I were to kind of compare some stars on here, let's say I have this one down here, I'll call star A. And I already plotted this one here that I called B, which I said was a lot like our sun. And then one up over here, which would be star C. Um, so there are several things that I can pull from the HR diagram. First, I can say, well, the absolute magnitude, if I look at the absolute magnitude of this star here, it's somewhere around a 12. And so recall that the bigger the number for absolute magnitude, the dimmer the star, and the smaller the number, the brighter. So this one would be a dim star. So stars at the bottom of an HR diagram are dim. Stars at the top of an HR diagram are bright. And then coming over here, I can see that it's towards the right end over here. So here's 3,000. It's less than 3,000. So this is a very cool star. And then over here, I have my hot stars. Okay. So immediately, just the obvious thing I should see is that star A is dim and cool. So that I can just read right off of the graph, but I should be able to infer more from it by saying, well, if it's a cool dim star, I know its color. It should be red. So this star here is going to be red. And then because it's cool and dim, I get a little bit of information about its size. It's probably a really small star. Okay. If I look at a star over here, like our sun, again, the sun is actually a white star. Um, it is right on the yellow white edge right there. And it is going to be bigger than this star. It's brighter than that star. Um, and it's still going to be fusing hydrogen into helium. And then as we look at this star over here, star C, it's a much brighter star, so it's very bright, and it's also very hot. So we should know that because it's bright and hot, it's going to be a big star, but we should also know that it's going to be a blue star. I hit on the wrong color there. So this is going to be a big blue star. Beyond that, I should also be able to determine something about how long they're going to live. So again, big blue stars exhaust their fuel very quickly. This one will live for a much shorter period of time than one down here. So again, they don't actually live, but fuse hydrogen into helium is what we're talking about when I say life. Okay, so this one will last for 100 billion years or so, this one about 10 billion years, and this one about only 100 million years. Okay, so then the main sequence represents the mature um, part of the star's life cycle when it is in, I would say, the prime of its life kind of thing. Um, and then as they get older and they start to age, they start to become either a giant or a supergiant. And you see that there's really no distinguishing line between them. They kind of phase from one to the other. So what we call a giant and a supergiant is just an arbitrary value that depends on size. So supergiants are bigger and giants are smaller, but they are essentially doing the same thing, that they are now fusing beyond hydrogen. So giants fuse helium into carbon. Okay, so a giant will be able to fuse helium and then fuses that into carbon, whereas supergiants will start fusing helium and they will fuse beyond helium all the way up to iron. And they will not fuse beyond iron because when they do so, they actually have a loss in energy. So iron marks the end of their ability to fuse to heavier elements. And once they fuse iron, they go supernova, and that's when the elements that are beyond iron are created in supernovae explosions. Okay. And then the last thing on here is our white dwarfs. That's these stars that are located down here. And these are really dead stars. So they're actually not really fusing anything anymore. So this marks like the end of a star's life cycle, if you will. So again, here are the stars that the main sequence stars are the healthy, mature stars. As they age, they become either giants or supergiants, and then they die. So there is a progression. Any of you that have been to the Denver Museum and played with the little simulator they have there where you can create stars, the larger the nebula that a star is formed from, the larger its mass will be, and the further up this main sequence it will be. So if you have a really small star down here, like Star A doesn't have sufficient mass to actually fuse beyond hydrogen. So a star like this will eventually just fade out. It will not become a giant or supergiant or white dwarf. Star B, like our sun does have sufficient mass to become a giant, and that's what it will do eventually. So when we did our solar system walk and we saw that the kickball was the sun, when the sun becomes a giant, it will expand out so that Mercury, Venus, and Earth will actually be inside of the sun. So imagine that that kickball is now the 26 paces that it was to the Earth. So it will dramatically get larger. Um, but the sun does not have sufficient mass to fuse beyond carbon. So once it has a fully carbon core, it will not be able to fuse anything beyond that, and then it will become a white dwarf. Okay, so a star like our sun goes from where it is in the main sequence now to a giant, and then down to a white dwarf. A star like this one up over here, like for example, Rigel. Rigel is a super hot blue star. When it builds up helium in its core and starts to fuse that, it will become a supergiant. And once it goes to a supergiant, it will go beyond carbon and all the way up to iron. And then again, once it kind of gets to that point, there are two possibilities, and neither one of those possibilities is represented on an HR diagram. So I'm just going to kind of set it off to the side. It will either become a neutron star or it will become a black hole. And what it becomes is completely dependent on the mass of its starting um, mass. So if it's a neutron stars typically are between 3 and 7 times the mass of our sun, and black holes are beyond 7 times the mass of our sun. Okay. So one other thing on here I just want to kind of point out, if I had a white dwarf here, and let's call that star D, a type of question that I might ask is, even though star A and star D have the same absolute magnitude or the same luminosity, if I were to say which star would be bigger, you should be able to answer that question. So I'll pause for a moment while you ponder that. And so the answer for which star would be bigger would be star A. And the reason I know that it's bigger is because they have the same brightness. In order to have the same brightness, this one that is cooler would have to be bigger. Okay, so that's the way I would kind of look at that. That this one's a really hot star. And so because it's so hot, it's going to be giving off intense light, but it has to be tiny in order for it to be as bright as this cooler star over here. Okay, so this just talks about most stars being represented on the HR diagram. Again, the exception would be the neutron stars and black holes. This is a little bit of a nicer HR diagram, kind of shows that progression from smaller mass stars up to larger mass stars, and showing how that increase in mass changes its color, changes its brightness, and will therefore change its life cycle, if you will. Then we have our giants and our supergiants over here, and then our teeny tiny little white dwarfs over here. So when we talk about stellar evolution, again, kind of going through the progression of from a nebula all the way to the end of a star's life. So a nebula is just a huge cloud of gas and dust in space. And so these are called the pillars of creation. And these are clouds that are many light years across. They're huge clouds. Um, and embedded in these clouds, you find stars that are being born. So you can see these bright dots inside these clouds. So something has to happen to cause the cloud to contract. Maybe there's a nearby star goes nova or supernova, and the shock wave goes out, or there's two black holes that coalesce and send out a gravity wave that cause the cloud to start to contract. And when it does contract, it heats up, and so it's important to note that when things are compressed, they heat up, and when things expand, they cool off. And so the heating of the nebula will eventually cause it to glow. So here we have what's called a protostar. So it's not a true star. Can we talk about prototypes, the first of something? So the protostar is glowing because it's hot. It's kind of like when I took that metal in class and I heated it up and it glowed red. Um, the protostar is just gas that's glowing because it's hot, but it is not doing what stars do, and that is fusing. So as it continues to heat up, if the core temperature reaches about 10 million degrees, then we'll get thermonuclear fusion. And at that point, the star is born. So when thermonuclear fusion begins, that's when you start to get that balance between gravity, which has been causing the cloud to collapse, and now you're going to get radiation, which is trying to push the star apart. Okay, so those are the two forces that will be acting on the star during its life cycle. Gravity will continually try to collapse the star, and radiation, the energy produced in the core, will continually try to blow the star apart. Eventually, gravity will always win that battle. And this point in the star, it's called a stable state. And again, this is when it will be on the main sequence of an HR diagram, and it will be fusing hydrogen into helium. Okay. Eventually, all good things come to an end, and the star will begin to run out of fuel. And when it does, it will start to get helium in the core. And this gets a little bit confusing. So it'll start to fuse the helium. And that fusing of helium will actually make the core temperature hotter, which will cause the star to expand. So the confusing thing is that the core, when it becomes hotter, will cause the outside of the star to become cooler. And the reason for that is when it expands, the same amount of energy will be spread over a much larger area, and so the surface of the star will cool off and it will become red. Okay, so the star expands, becoming a giant or a supergiant, again, dependent on the size of it. And this marks the old age part of the star. So again, it's fusing helium into carbon and beyond. Eventually, though, it's gonna stop fusing, and gravity will ultimately win the battle, and it will collapse the star. So it exhausts its nuclear fuel, fusion will stop, and gravity will collapse it. And when it does, there are three possible outcomes for the star. So in this right here, it's showing the outer layers being thrown off, and a star like the sun will become a white dwarf. So this is a picture here of a white dwarf that's being left behind. The white dwarf would be at the center, and this would be what's called the planetary nebula that goes outside of that. If it is between 3 and 7 times the mass of the sun, you will get a neutron star. And so this is a star that's composed entirely of neutrons. The electrons have been driven into the nucleus, converting the protons into neutrons. And if it's beyond 7 times the mass of the sun, it will become a black hole, and it will literally tear itself off from space time. Okay, so those are the three possible outcomes, and it's all dependent on the initial mass of the star. Okay, so now we get into the math part. And so this formula right here, it will initially look very confusing, but it's actually a pretty simple formula, and it relates the lifetime of a star to the lifetime of the sun. And it compares that to the mass of the star and the mass of the sun divided by the luminosity of the star compared to the luminosity of the sun. So I realize that looks really confusing there, but if we just look at this as a ratio, so this T over T solar is just a ratio of the life of the star compared to the sun. So, in other words, if I had something that had 5T solar, and that's the symbol there for solar. So, that would just read as it lives 5 times longer than the sun. If I had something that was, say, zero point 0.4 T solar, that would indicate that it lives for about zero point 0.4 times as long as the sun. Okay. So then this ratio right here is the mass of the star compared to the mass of the sun. So once again, if I had something that was, say, 3M solar, that would indicate that it has 3 times the mass of our sun. If it was a decimal, like, say, 0.2 M solar, it would be zero point 0.2 times the mass of the sun. And the last thing here, the luminosity. So if something's had, say, zero point 0.5 L solar, that would indicate that it's half as luminous as the sun. It's half as bright. Okay. And then this right here, this statement here, that the sun lives for about 10 billion years. So that's what that T solar equals 10 billion years. So if I'm going to apply this formula for this question here, a star is 20 times brighter than the sun, and it has a mass 4 times greater than the sun. So really all I'm going to look at is this 20 and this 4. And that's what I'm going to plug into this formula right here. So I can kind of get rid of this M over M solar and just say, well, 20 times brighter, that's the L. The 20 compared to the sun, well, that L solar is just 1. So 20 over 1 is just 20. So I'm going to have in the bottom, I'm going to have 20. So my denominator is 20, and my numerator is going to be the mass. Well, the mass is 4 times greater than the mass of the sun, so I'm just going to have 4. 4 over 1 is 4. So if I want to know the lifetime of the star compared to the life of the sun, it's equal to 4 divided by 20. 4 divided by 20 reduces down to 1/5, which is 0.2. So 0.2 times as long as the sun. And that's all I would have to do for that. So the star will live for 0.2 times as long. The next part of the question says, well, how many years is that? Well, I just come up here and instead of T solar, I see that that's 10 billion years. So if I substitute in 10 billion years for T solar, 10 times 0.2 is 2. So the star would live for 2 billion years. Okay. And then coming to this one, what is the comparative mass of a star that is 4 times the luminosity of the sun and lives 4.4 times as long as the sun? So I would simply say zero point 0.4 for the lifetime of the star compared to the sun is equal to the m, which I don't know. So I'm just going to put m divided by, and then the luminosity, it's 4 times the luminosity, so 4 here. So then I can manipulate this formula. I'm going to solve for m. So I'm going to have m equals, and then I multiply both sides by 4. So 4 times 0.4. Sorry, that's supposed to be a decimal there. And that is going to equal 1.6. And that would be times the mass of our sun. So it's 1.6 times more massive than our sun. And that's it. Okay, this is the very last part. Sorry about this. I know it's a long video, but so here we have 5 stars, star A, B, C, D, and E. You're given the absolute magnitude, the apparent magnitude, and the temperature. So the first part of what I'm going to ask you to do is determine what kind of stars these are, and then I'm going to ask you to put them in a relative sequence of how far they are from the Earth. Okay, so the first thing is to identify what information I'm given that's going to let me identify the type of star it is. So hopefully you recall that an HR diagram will allow you to do just that. So here's the HR diagram that I'll be using to kind of show you what these stars are. So remember that HR diagrams plot stars according to their absolute magnitude and their temperature. Okay, so for star A, the absolute magnitude of 4.8 and 6,000. So 4.8 is pretty dim and 6,000 is kind of mid-range for temperature. But if I look over here, 4.8 is right around 5. So it's going to be around this area here going across. And then 6,000 is right here. So if I were to go to the point where they intersect, right here would be where star A is. Okay. I come back up here. Star B, an 18 is really, really dim. In fact, that's below my HR diagram, but 18. And then 2800 is also really, really cool. So if I come back down here, 2800 is about right here, and then 18 would be even below it. So I'm just going to put it right around here is where star B would be. Then I'm going to look at star C. A 14, once again, that's very dim, and 17,000, that's actually really hot. So it's a hot, dim star. So if I look over here, 17,000 is going to be around here, and then the 14 puts it right around over here. So that, hopefully you can see, is going to be a white dwarf, and that was star C. If I look at star D, a -8, that indicates it's really bright, and a 3000 is going to be really cool. So we have a really cool, really bright star. And so hopefully from this, you can see that that's going to be a supergiant. So that's star D. And then the last one, 24,000 degrees, that's very hot. And a -6 is very bright. 24,000's over here, -6 about right here. So this star is on the upper edge of the main sequence, and that will put it right there, star E. Okay. And then kind of knowing where they are. So again, star A was right here in the middle. That's going to be a star just like our sun. Okay. Star B was down here. It's going to be a little teeny tiny red star. Star C, it's going to be a dim hot star. That was going to be our white dwarf. Star D was a really bright cool star. That was going to be a supergiant. And star E was a hot bright star. That's going to be a blue, big bright blue star. Okay. So that's the first part right there. And then you'll see that I put the Earth here. I put a line 10 parsecs away. And then I'm going to ask you to identify, and this is going to be the tricky part, their relative distances from the Earth. Okay. So in order to do that, I need to compare the absolute magnitude and the apparent magnitude. Okay, so recall that the absolute magnitude is how bright the star truly is from 10 parsecs away, and the apparent magnitude is how bright the star appears from Earth. And so by comparing those two numbers, I can get an idea of the distance of the star. So there's a couple of ways to kind of go about doing this. So first off, if I look at the apparent magnitude, this is what I'm going to kind of use as my comparison because I'm going to be plotting these stars' distance from the Earth. So a -26.5. Remember that negative numbers are really bright. So a -26.5 is incredibly bright. The absolute magnitude is actually kind of dim, a 4.8. So I can identify that the star appears to be brighter. It appears to be brighter because it is closer than 10 parsecs. So I know that star A is closer than 10 parsecs because it appears brighter than it actually is. Okay. Same thing kind of holds over here. If I look at star B, remember that a smaller number, and this is what I normally do, is I draw an arrow down to the smaller number, or I draw an arrow to the smaller number. So my down arrow indicates it's closer, and an up arrow would indicate it's further. Okay, so if I look over here, 18 and 14, I'm going to draw my down arrow, and that's going to tell me again that 14 means it's brighter because 14 is a smaller number. It's brighter, and that is because it is closer. If I look at star C, you'll see that the 14 here and the 14 here are the same number. Well, what does that tell me? That tells me it appears to be the same brightness from Earth as it does from 10 parsecs. That indicates it is 10 parsecs away. So I can come over here and say, well, star C is 10 parsecs away. It's going to be right on this line. So I'm going to put it right there. I know exactly how far that star is. And then I'm going to come back over here. I'm going to look at star D. Recall that negative numbers. Again, that -8 is really a small number. It is smaller than 0, so it is actually brighter than it appears. It is, so I could say it the other way would be it appears dimmer than it actually is. Why does it appear dimmer? Because it is farther away than 10 parsecs. Coming over here, I have a -6 and a -3. The -6 is the smaller number. Therefore, it appears dimmer than it actually is. It appears dimmer because it is farther away. Okay. So now when I place these, I'm I'm going to use this 10 parsec line that I made, and I'm just going to kind of think of this as being like a number line. If this is my 0 mark, then as I go to the right and I go to the left, the numbers will increase. Okay, so yes, these will increase in the negative direction, these will increase in the positive direction, but just kind of think of it like that. And then to identify which of these two stars is closer and which of these two stars is farther, I look at the difference between these two numbers. So the difference between 4.8 and negative 26.5, because they have different signs, I add them together and I get 31.3. Well, 31.3 is going to take me very far from this 0, right? And again, it's closer. I already identified that. So if I come 31.3 units over, if you will, that's going to put it over here somewhere, okay? If I look at this one, the difference between 18 and 14 is only 4. So I would come 4 units over, okay? So if I place star A, which was 31 units over, I'm going to put it way over here. And if I place star B, I'm going to place it right there. So now I have a relative order of these first 3 stars. So now I come over here and I'm going to do the exact same thing. I identified the difference between 0 and negative 8. The difference is 8. And the difference between negative 3 and negative 6 is 3. Same sign, so I just take the difference between them. So again, kind of moving away from this 0 line, if you will, I'm going to go 3 units over for star E, and I'm going to go 8 units over for star D. So star E would be placed, star E would be placed here, and star D would be placed, if I can do it, right there. And so that would be the relative order of those stars. Okay. Some other things that will pop up as you do the stellar lifespan and distance sheet. When I look at the absolute magnitude, if I were to say which of these 5 stars is the brightest star, I would look at the absolute magnitude and identify the smallest number, and I would say that star D has the smallest absolute magnitude, therefore it is the brightest star. If I said which one would appear the brightest, I would identify from the apparent magnitude that a negative 26.5 appears the brightest. That would be this star here, star A. Okay. If I were to say which of these 5 stars will have the longest lifespan, I would say star B. Why? Because it's a little teeny tiny red star, and we said that those stars have the longest life. If I said which of them would have the shortest life, I would say, oops, that got dark. I would say star E, because it was the bright blue star and they burn through their hydrogen very quickly. So again, what I want you to do is concentrate on the first 2 assignments, and then this we will be able to finish up when I'm in class next time. I hope that helped, and I will see you guys next class.